Welcome to Physics with Joe. In my last video, I gave an introduction to projectile motion, where I talked all about what projectile motion is and the relevant equations for projectile motion. If you haven't watched that video yet, I highly recommend you do that first. I'll put a link in the description below. Today, I'm going to do a detailed example problem where I illustrate some of the types of questions you may see in any projectile motion problem. So without further ado, let's launch right into it. This example problem states the following. A 5-kilogram pumpkin is launched at 15 meters per second at a 55-degree angle from a height of 0 meters. Air resistance is negligible, so we can use the equations of projectile motion. And what we want to know are 6 different things. A, how long does it take to reach the highest point? B, how high does it rise? C, how far does it travel horizontally? D, what is its height when it has traveled 16.35 meters horizontally? E, what is its speed when it has traveled 16.35 meters horizontally? And finally, F, what is its minimum speed while in the air? These are typical questions you may see in any projectile motion problem, so let's see how to solve them. Before I jump into solving this example problem, let me remind you of the equations of projectile motion. Remember, projectile motion is really a combination of vertical motion at a constant acceleration and horizontal motion at a constant velocity. So vertically, we have the exact same 4 equations that we had when dealing with free fall. And we know the acceleration in the y direction near the Earth's surface is negative 9.8 meters per second squared. Now horizontally, since the acceleration in the x direction is 0, the 4 equations of constant acceleration in the horizontal direction really reduce down to 2. The first one really just says that Vx equals V naught x. Whatever horizontal velocity this object starts with, it will have the entire time it's in the air. The second equation is really the big equation that we have in the horizontal direction. It says x minus x naught equals v naught x times delta t. Now that we know the equations of projectile motion, let's solve this example problem. This pumpkin is being launched at 15 meters per second at a 55-degree angle from ground level. And what you'll see in this animation is 3 different arrows. The thick green arrow represents the velocity of the pumpkin as it's moving through the air. The horizontal arrow gives the horizontal component of the velocity, and the vertical arrow gives the vertical component of the velocity. So let's fire this pumpkin and see what happens. Notice that the horizontal component of the velocity does not change. It's only the vertical component of the velocity. Quick question. If instead of firing a pumpkin, I fired a car, would I expect the path of the car to be any different than the path of the pumpkin? The simple answer is no. If there is no air resistance, it does not matter the mass of the object or the size of the object. All objects would travel the exact same path given the same initial conditions. So I fire this car. Woohoo! Bullseye! So let's change this back to a pumpkin again. Let me fire it again. And if I just step through this, if you notice that on the way up, the velocity in the y direction is pointing upward, so it's positive. On the way down, the velocity in the y direction is negative because the object is moving downwards. If you notice, at the very highest point, there is no velocity in the y direction. And that is really what defines the highest point when we're talking about projectile motion. It's when the velocity in the y direction is 0. So let's start calculating these different quantities. Anytime you're doing a projectile motion problem, you're always going to need the initial velocities in the x and y directions. So I like to just start by calculating those. Initial velocity in the x direction is initial speed times cosine of the launch angle the initial velocity in the y direction, initial speed times sine of the launch angle. In our case, we have the initial speed is 15 meters per second. The launch angle is 55 degrees. What we get is that the initial velocity in the x direction is 8.60 meters per second. The initial velocity in the y direction, 12.28 meters per second. Now I'm keeping an extra significant digit or two so I can get my calculated answers to match those that you can get from the animation. The other thing that you want to do to begin with is define where your origin is. So defining x naught and y naught. I'm going to define my origin as where this object starts off at, where the pumpkin starts off at. So I know my initial position is 0 meters in the y direction, 0 meters in the x direction. I also know my initial velocity in the y direction is 12.28 meters per second. My initial velocity in the x direction is 8.60 meters per second. Well, let's start at the beginning. A, how long does it take to reach the highest point? Remember, what defines the highest point is when the velocity in the y direction is 0 meters per second. So we're going to solve for what is delta t when the velocity in the y direction is 0 meters per second, which it is at the highest point. So I have Vy is 0 meters per second. I do not know delta t, and I do not know y, which would be the height at the highest point. Well, the equation I'm going to use that has my known and unknown quantities, in this case we do not know delta t, is Vy equals V naught y plus Ay times delta t. We know at the highest point the velocity in the y direction is 0, so this equation reduces to 0 equals V naught y plus Ay times delta t. Solving for delta t, what we get is the elapsed time from launch to highest point is equal to negative V naught y over Ay. So plugging in our values, we get delta t equals negative 12.28 meters per second divided by a negative 9.8 meters per second squared. Do the math, and what you'll get is it takes 1.25 seconds to reach the highest point. So now we know my elapsed time is 1.25 seconds to the highest point. And now we can use that to figure out how high does this object rise. What I'm really looking for is what is y when t equals 1.25 seconds. Well, I have a few different equations I could use to calculate this. I could use y minus y naught equals v naught y delta t plus 1/2 ay times delta t squared. I could also use vy squared equals v naught y squared plus 2ay y minus y naught. Or I could use y minus y naught equals 1/2 v naught y plus vy times delta t. It doesn't matter which one you use. Let's just use the last one. So I have y minus y naught equals 1/2 v naught y plus vy times delta t. I define my initial position to be 0. I know that Vy equals 0 at the highest point, so this equation reduces to y equals 1/2 V naught y times delta t. And if I plug in my values, I get y equals 1/2 times 12.28 meters per second times 1.25 seconds. What I get is the highest point that this pumpkin reaches is 7.69 meters. Now for C, how far does it travel horizontally? Well, one of the key things in projectile motion is if the object lands at the same height it was launched at, then the total time in the air is twice the time it takes to get to the highest point. So if it takes 1.25 seconds to reach the highest point, that means it's going to be in the air for a total of 2.5 seconds. So I can put in for delta t here 2.5 seconds, and this is the total time in the air. So the only real equation I have in the x direction, so this would be for part C, is x minus x naught equals v naught x times delta t. My initial position in the x direction is 0, so I get x equals v naught x times delta t. Plugging in my known values, what I get is my initial velocity is 8.60 meters per second. It's in the air for a total of 2.50 seconds. What I get is it travels 21.5 meters horizontally before hitting the ground. Part D. What is its height when it has traveled 16.35 meters horizontally? Now, the way the horizontal and vertical equations are connected is through elapsed time delta t. So if I want to know what is its height when it's traveled a certain distance horizontally, what I first need to do is figure out what is the time it takes to travel that distance horizontally, and then I can use that time to figure out the height. So we know that x naught is 0, x is 16.35 meters. The initial velocity is 8.60 meters per second in the x direction, and delta t is what I'm looking for. Again, in the x direction, there's only one equation. It just is x minus x naught equals v naught x times delta t. My initial position in the x direction is 0, so what I get is x equals v naught x times delta t. Solving for the elapsed time, we get delta t equals x divided by v naught x. So 16.35 meters divided by 8.60 meters per second. What we get is it takes 1.9 seconds to travel a distance of 16.35 meters horizontally. And now what I can do is figure out what is the y value, what is the height at 1.9 seconds. So now I know my elapsed time is 1.9 seconds. Vy I don't have, but I don't need at this point, and y is what I'm looking for. So in this case, I do not have my velocity in the y direction at 1.9 seconds, so the only equation I can use is y minus y naught equals v naught y delta t plus 1/2 ay times delta t squared. My initial position in the y direction is 0, so this reduces to y equals v naught y delta t plus 1/2 ay times delta t squared. Plugging in our known values, I have y equals 12.28 meters per second times 1.9 seconds plus 1/2 times negative 9.8 meters per second squared times 1.9 seconds squared. Do the math, and what you'll get is y equals 5.64 meters. That is the height at 1.9 seconds when the pumpkin has traveled a distance of 16.35 meters horizontally. E. What is the pumpkin's speed when it has traveled 16.35 meters horizontally? Keep in mind that speed is just the magnitude of the velocity. So if I ever want the speed of an object, what I need is the x component of the velocity and the y component of the velocity at that time. And the speed is just going to be the square root of vx squared plus vy squared. So what I need is what is vx at t equals 1.9 seconds? What is vy at t equals 1.9 seconds? Well, keeping in mind that velocity in the x direction doesn't change. I know my velocity in the x direction at any time is going to be the same as the initial velocity in the x direction, 8.6 meters per second. Now to figure out the velocity in the y direction, I'm going to use vy equals v naught y plus ay times delta t. Solving for vy, what I get is vy equals 12.28 meters per second plus a negative 9.8 meters per second squared times 1.9 seconds. What I get is the velocity in the y direction at 1.9 seconds, which is when it has traveled 16.35 meters horizontally, is negative 6.34 meters per second. The negative sign indicates that the object is moving downwards vertically and it's already crossed the highest point. Now I can figure out my speed. It's going to be the square root of Vx, which is 8.60 meters per second squared, plus negative 6.34 meters per second, whole quantity squared. And what you get is the speed is equal to 10.7 meters per second. Now this problem didn't ask for this, but what happens if you wanted to know what direction this object is moving at that time? Remember, velocity has both a magnitude, which is the speed, and a direction. If I want the direction, then what I'm going to solve for is theta, which is the inverse tangent of the y component of the velocity divided by the x component. Well, let's just solve it. In this case, we know that at t equals 1.9 seconds, velocity in the y direction is 6.34 meters per second. Velocity in the x direction, 8.60 meters per second. And what I get is theta equals negative 36.4 degrees. Last but not least, what is the minimum speed this pumpkin has while it's in the air? Well, keeping in mind that speed is just the square root of Vx squared plus Vy squared. And the velocity in the x direction does not change the entire time it's in the air. My minimum speed is going to be when Vy is a minimum. And we know that Vy equals 0 meters per second at the highest point, which means my minimum speed is going to be the square root of Vx squared plus 0 squared. That's going to happen at the highest point when Vy equals 0. So my minimum speed is just the x component of the velocity, which is always going to be equal to the initial velocity in the x direction, which in this case is 8.60 meters per second. So this pumpkin never has a speed less than 8.6 meters per second while it's in the air, and that minimum speed happens at the very highest point when Vy equals 0 meters per second for a split second. Well, that is it for this example problem. Let's just take a quick look at the animation and see if our results were correct. The simulation I was using for this video came from the PhET website, and the PhET website has a collection of hundreds of different simulations in physics and chemistry and other subjects. If you want to find this particular projectile motion simulation, you can just go to Google, type in PhET projectile motion, and the very first site that comes up will be the one that you want. I really like this particular simulation because you can make up your own projectile motion problems and double check your work. For example, we found that it took 1.25 seconds to reach the highest point, and the height at the highest point was 7.69 meters. So I could double check my work by making up a problem and then seeing whether or not my answers make sense. We also found that it traveled a total distance of 21.5 meters, and when it traveled 16.35 meters horizontally, the height was 5.64 meters. Now, this particular simulation doesn't give you any information about x and y components of the velocity or speed, but in terms of calculating how far it's going to go, how high it's going to rise, this is an outstanding simulation. Well, that is it for today's episode of Physics with Joe. My name is Joe McCullough. Thank you so much for joining me. And until next time, I still need a catchphrase.